Did they publish the active cases in SIU today? Yeah, I checked in the morning. I was just curious. Seems like it is better, much better than what I expected. That's good.
No, they did not take it.
Okay. Hello, Matt.
Hello.
Okay. It's only you, so let's wait for a minute or so. Or it's not, I should say two here and you there, virtually only you. So how was the midterm? Any comments in general? The grading and midterm? Oh. Do you think the questions were harder because it was take home?
Probably, but understand.
I didn't try to make it too hard either because I cannot give it too simple either because it will be available. Or I depend a lot on my notes also in this classroom. I try to repeat things from the homework and other places. But I couldn't because then it would be much. But then time is the limit usually there. Here you get to think a lot. So, focus on that.
I thought it was pretty constructed. I realized I made a very silly mistake.
Repeat, you broke off first few words.
Oh, sorry. I said I thought it was very well constructed.
Okay.
I realized I made a very silly mistake in just my mathematics on one of them, but I thought it was well done as similar to what we've done, but hard enough to where, I mean, it's what you'd expect for a take home, but not so hard that we have no idea how to do any of it.
Okay, that's good to know. Any other comments on Curtis and Matt?
No.
I just got here. I didn't know what you're talking about.
I was saying, how was a midterm? So was it reasonable because it was a take home? I tried to do it a little different in the sense that I repeat a lot of questions from the homework usually, if it was a classroom exam. And here I had to build it a little newer, but at the same time, I didn't make it too hard. So
it was pretty reasonable to me. It wasn't too bad.
Good. Okay. So let's. Before I forget, I should mention that the video for last class did not come up because I think there was a disconnection in the beginning. So at that time, the recording went switched off, and then we never switched it on again. So there was no recording for last class. So whoever depends on it, I cannot have that. I cannot go in the past. But what you could do is that if you're really particular about these videos, you could, especially those who are sitting in front of the computer, if you don't see the recording button on the left, that means it's not getting recorded. It's as simple as that. So just remind me of one of us can do this. Yeah. So how many of you depend on the recording?
I wouldn't say depend, but yeah, it is nice to have.
Okay. Matt, you were saying something?
I mean, I still take notes and everything, so I have everything, but it is nice to be able to go back and kind of hear what you said again to help kind of reinforce what my notes say.
Yeah, understandable. I'm sure it's helpful, but just those who really think it's relevant, just pay attention to recording. That's what I can request. So, okay. Few things about the midterm. So remember, so these are the total grades, not the midterm. So this is midterm plus homework, right? So total is midterm plus homework, and grades are, some of you are doing really good in the course, so it's 99.8, 90, that's pretty much 100 as far as I'm concerned. So it's 91.9, and then there's 83.5, 74, and 68.5. Remember, we agreed that we will curve. So curve is equal to total plus the 100 minus total. Right? So I return back whatever you lost. This is what you lost. I return back, but I don't give you the full grades back. I give you a percentage of it back, and this time I gave 10% back. So it's 0.1. But then to get the whole thing, you also need to have done good in the extra credits. So that's where your extra credit comes in. So this is extra credit out of 0 and 1. Right. So so once you take care of that, and here these are the extra credits. So it's Y 0.8, 2.7. And that inflates your grade. So this is pretty much, so this is 99.9, 99.3, 92.5, 4.6, 70.7. So that's A's, that's a B, and that's C that we said. But this is just first part of the course. There is significant amount of time to boost your grades. So yeah, that's, I think you guys know enough of these things. Any general comments on that? Any questions you might have? Concerns, or if you want to talk separately, feel free to just send me an email and we can talk on Zoom. Okay, so homework, that is homework 6, which is due Monday. There are a lot of questions that show up in the homework problem, but not everything is due. Right? Only few of them are due. The rest of it is for practice. So, and if it has practice problems, they were not just constructed out of nowhere. They were asked in exams before. So I asked something in the exam. I just collected that. So in the years, it has become some few problems, and that's what these practice problems were asked in past exams. That doesn't mean that I'm testing you guys on that, but it gives you a feel for yeah, it should be worth attempting. And we have midterm 2, which is October 9. And midterm 2, as of now, by default, let's keep it in class. Like what we had last week, we will have it in class, but like last week, if necessary, we will change it. So be prepared to be having the exam in class. Okay. we were discussing electrostatics. We just began electrostatics. Electro means anything related to charge, and statics means that things are at rest. And the equations governing electrostatics is that the divergence of the electric field is equal to Q, charge density. Let me explicitly write the X dependence also now. So this is R. There should be time here also, but I've put it static, so that's no time dependence in there. Charge density, which is charge per unit volume at any point in space. The second equation that governs this is that del cross E, electric field, which is again having spatial dependence, is equal to 0. In general, this is a Faraday's law. The change in magnetic field creates electric field, but change in magnetic field with time is 0 because we are doing statics. There's also one more equation. What this says is that given a charge distribution, if it is static, then the electric field produced is governed by these two equations. That is also, you can ask, if there is an electric field, what is the force it exerts on another charge? And that's given by the Lorentz force. And since we are not having any magnetism, there is only one simple equation, that the force is Q times the electric field. So it is good to point out that if this was charge 2, I say charge 2 because usually the electric field should be imagined to be produced by another charge. So that's a charge there. And this is the position of charge 2. Right? The electric field at the position of charge 2. So that's crucial. That's a conceptual point in there. That is force, but we have charge density in here. So, that's a force on a charge. Typically, we would like to know what is the force in terms of charge density. Charge density means a lot of charges, right? We just have to add up all the forces. Instead, we can say force per unit volume. So let's call force per unit volume, which we will say is the small letter F, and that will be given by, so that is now at a point, right? So force is typically on a charge, but force density is at a point. That's equal to charge density times the electric field at that point. Okay. Very same idea, it's just that we divide it out by the volume. Again, remember that there is QV cross B here. If there was a magnetic field, that adds on to them. These are two different descriptions. Here we are saying, give me the charge, there is an electric field produced. If there is an electric field, there is a force on another charge. Typically, the charge cannot exert a force on itself by creating an electric field. So that's a question we are dealing with. Last time we said we tried to understand what is the meaning of this curl of the electric field being 0. We said that means that this is a conservative field, and this implies, remember that in Newtonian physics we talk about forces, and if the curl of a force is 0, that means that there is a potential energy associated with it. Force is interpreted as the change in energy with respect to distance. It's a gradient of the energy. So this implies that there is an electric potential. It's very special. It's a very significant point that not every force you can think of has a potential associated with it. So this is a field now. Field is associated field multiplied by the charge is a force. So here is a quantity where we can associate a potential associated with it. And as we discussed last time, that is gravitational force that has this potential energy associated with it. Electrostatics, that's pretty much as two fundamental forces. But a third quantity that you do come across is the spring force, which is also having a potential energy associated with it. But it's all one-dimensional, so it's not very fundamental. It's used to model many forces, but we don't usually have a quantity or a specific force that is like a spring force. It is used to model various systems. So two forces that have potential energy associated with it is electrostatics and gravitational potential energy, which you have come across. As you proceed, you will see a few more, not many actually, forces that have potential energy associated with it. So electrostatics is such a quantity, and this will be called a electric potential. And it is, of course, dependent on the position, right? This is also position dependent. The gradient of the negative gradient of the potential is the electric field. If that is the case, I can substitute the electric field in there. So this implies this, and this I can substitute in there. And that gives me an equation for the electric potential, a differential equation for the electric potential. So substitute one in the other, and I have divergence dotted with usually we are familiar with taking derivatives in one dimension. Now this is a three-dimensional derivative. That's a gradient, and double gradient, which is basically the divergence of the electric field. Here this becomes the Laplacian. That's equal to 1 over epsilon naught times charge density. This operator here is written as del square, gradient dotted with the gradient itself, and that's your electric potential, and we have 1 over epsilon naught times your charge density. This is called a Laplacian operator. Del square is equal, so it's not a vector, notice vector dotted with a vector becomes a scalar, and this is simply second derivative with respect to x squared c squared. This acting on a function which is dependent on x, y, and z has to give you the charge density, but we are inverting the problem in the sense, give me the charge density and what is electric potential. That's what we're asking, which is to say that find the function whose second derivative in the sense of the Laplacian, there are three second derivatives, gives you the charge density. That's the quantity, that's what we are asking. It's often useful to work in other coordinate systems. In this course, in principle, there are lots of coordinate systems we can work with, but very few have neat solutions. And two of the problems which are very useful are three, I should say: spherical symmetry, cylindrical symmetry, and planar symmetry. So these are the three symmetries we should keep an eye on. Whenever there is planar symmetry, this helps. Rectangular coordinates is very useful. The way to see it is that these are planes, right? When you think of coordinates, these are planes. Coordinate systems built out of planar surfaces is the rectangular coordinate system. If you're working with cylindrical coordinate system, the Laplacian, so maybe you should write this down, right? This is the Laplacian. So we'll be interested in solutions of the Laplacian, which is a different partial differential operator. In cylindrical coordinates, this takes the form 1 over rho d by d rho rho d by d rho plus 1 over rho square plus e by dz square. We won't be using this immediately of now. This is for cylindrical coordinates, rho phi z, right? So this is cylindrical. So this is rectangular coordinates. This is cylindrical. And from your work in math methods, theoretical methods in physics, you will have a rough idea of how these operators combine. You might not have too much experience in using it, but you should have a rough feel for what that is. If you are in spherical coordinates, this takes the form 1 over r square and there's 1 over square sine theta and finally, oops, and this is spherical. And you can do this in a few more coordinate systems, not many actually. You need to have a lot of symmetry to be able to solve these differential equations. And of course, spherical symmetry will be our favorite. First will be planar geometries, and then will be spherical. And we'll limit ourselves to that. We won't even go to cylindrical coordinates. Spherical itself will be sufficiently complicated that we will, in this course, we won't go beyond it. So you will see either we are talking about surfaces that are planar, or they will be point objects, or they will be spherically symmetric. We will talk about a solid sphere, charged solid sphere. So that's the equation. So let's do some examples, right? So our equations become the Laplacian equation. So we have so this is given. So the charges that are given, and this is to be determined. If you don't like, if you want it more explicitly, this is basically x, y, z. Right? That's just a short form for writing the 3 variables x, y, and z. Right? The electric potential is dependent on the coordinate where you're in. So the strategy is the first step is to given the description of the charges, mathematically describe your charge density or give a mathematical description of rho, reasonably precise. So if you're, for example, if there is a point charge, you should be able to describe it mathematically. So that's the first thing we would like to do. Second is solve this differential equation. So solve the partial differential equation. Equation 4 or 5 for the electric potential. would be, we are interested in the electric field usually, so this gives you a solution for phi. Find electric field by taking the negative gradient of the electric potential. And from that point on, you can do the physics. You can find the force acting on another charge, or what is the energy stored in the electric field, and so on. And that you can analyze the problem. Right? Then fourth one is the analyze. That's right. Okay. Most of the time in this course, we will try to understand, if not actually literally solve, that you will see in mathematical methods courses or in a mathematics course. I will show that using very simple techniques, which is called the Green's function technique, we can actually solve for phi in reasonably simple, using simple methods, which is basically the law of superposition of potentials. And once we have that, we can find the electric field immediately. So let's do an example, right? How does this work, right? So example. So let's say there is a single point charge. It's not point charges, that is single point charge at position RA. So single point charge Q at position RA. That's a description of the problem. Go here, we first have to get the mathematical description of a charge sitting at RA. So charge density, right? So the first step is to get the charge density. And it will play an important role when it comes to the Green's function description. So we will say that's charge density. So charge density for a point charge. This is the coordinate. This is not the position of the charge. This is the position of the charge. This is a coordinate in space. Where in space are you measuring the charge density? And charge density, we already said, can be described in terms of delta functions. So this is Q times delta function. And typically we write it in short form this manner, R minus RA. But what this is a short form for Q times the position on the x-axis is XA. Position on the y-axis is Y minus YA. It's not on the y-axis, the coordinate, right? For example, if the charge is down here, that's your XA, that's your YA. So it says that X is equal to XA, Y is equal to YA, and Z is equal to ZA. So as a first step, that should be pretty straightforward. If there is a disk or a sphere, then we have to be a little. We should have a little more experience, but you will see that with a few of the systems that we'll consider, a few of the examples, you will know exactly how to write the charge density almost immediately. What's the Laplacian or the partial differential equation we are talking about? So this is negative Laplacian of the electric potential is equal, it's a single charge, so it is Q, that's an epsilon also, don't forget that. Q over epsilon naught, and that is a delta function. Notice the difference between the two positions. This is the position, or this is the coordinate space, which point in space are we interested in talking about, and this is the position of the charge. So make sure that is very clear. This is position S at an observation point, let's say. So this is an observation point. like it's a coordinate in space, so observation point. This also is an observation point, and this is a position of charge. Which is the source. We will often use the word source. So this is a source point. Where is the charge sitting? That's a source of the electric field. And somewhere outside the charge, you observe the electric field. So that's your observation point. If you want to write this equation more explicitly, this is d by dx squared plus d by dy squared phi of x, y, and z equal to q over epsilon naught times x minus xa, y minus ya times z minus ca. Right. And that's not a simple differential equation to solve for. In fact, this, if you remove this q over epsilon naught, so let's now change the very similar, I mean, the content is exactly the same, but we are now going to define a Green's function. So this is clear, right? These two are the same. So let me use this notation. So this is a short form notation. This is negative of the Laplacian. Instead of the electric potential, now I want to define what is called a Green's function. Instead of phi, I say this is r. And it also depends on where the position is, the charge RA, if you want. So let me call that R prime. I want to keep it general, not really for this problem. And forget about the Q. Basically, I'm setting Q is equal to 1, epsilon naught equal to 1. R minus R prime. Okay. This is the Green's function. So G is the Green's function for the above differential equation. You would notice that most of the time when you have done partial differential equation before, very rarely do you come across differential equation which has a source on the right hand side. Usually you do homogeneous differential equation. And here we will be working with inhomogeneous differential equation, so it is one step further. But we do need the solutions for the homogeneous differential equation. Once we know the solution for the homogeneous differential equation, which means this is equal to 0, then we can write down the solution for the inhomogeneous differential equation. So this will be the Green's function. So in physics language, what is Green's function? Green's function is the electric potential for a point charge of unit magnitude, and in a vacuum where epsilon naught is equal to 1, or in a unit system where epsilon naught is equal to 1. So Green's function is the electric potential due to a point charge of unit magnitude. If that is the case, what is the solution for this? What is the Green's function for this differential equation? So think in terms of what you did in introductory level physics. So again, I'm saying Green's function is the electric potential due to a point charge of unit magnitude in a vacuum or in a unit system where epsilon naught is equal to 1. Electric potential due to a point charge. What is that equal to? Q over R, right? And Q I said is 1. So it is 1 over R if I'm talking about the Green's function. So we all know that electric field is equal to 1 over 4 pi epsilon naught times 1 Q over R square. And that is the R hat. This should be familiar idea. And the electric potential associated with this is simply 1 over 4 pi epsilon naught times Q over R. No R hat in here. So this is a small extra credit problem. Extra credit. Evaluate negative gradient of phi. Evaluate the gradient of phi. Remember that use your methods that you learned in the first few weeks. In one of your homeworks, we did gradient of 1 over R. You can use those results here. So there is a constant Q over 4 pi epsilon naught that comes out. In fact, we know what it should be. It should be the electric field, right? Negative gradient of electric potential is the electric field. This should give you that, but you have to show that. So the answer is supposed to be this, but you should be able to show that negative gradient of this is equal to. Yes, so because notice here, an electric field is negative gradient of the electric potential. So it's expected to be exactly this. So verify that. So using that, it is clear that the Green's function, is 1 over 4 pi times 1 over, this is 1 over R, but it is 1 over R when you place the charge at the origin. But here it is not at the origin, it is displaced from the origin, and you have R minus R prime. So we know the solution now, right? So we were solving for this. We immediately know this should be the solution, but we want to do this in a slightly more general form so that in the next example it should be useful. So we want to introduce a general solution here. So this, when there is no source, is called the Laplacian differential equation. This is Laplacian differential equation. And if you have a charge associated with it, so these are two differential equations. So there is a source here. So let me specifically write this is Q over epsilon naught problem that we are dealing with. That's called the Poisson equation. Differential equation. So those are two differential equations. And a Green's function associated with this differential equation is called G of R, R prime. So basically, replace the source with just the delta function, and that's and this is the Green's function for Poisson equation. And in between, we will spend some time figuring out how exactly to solve this differential equation, but we will try to restrict ourselves not to go into too many mathematical details because you will see these differential equations coming in different places. Okay, so that's your three differential equations, and in general, if you know the Green's function, you can actually calculate the electric potential. So in terms of the Green's function, your electric potential is, so this will be our primary equation. You can say the law of superposition, as I will describe in a few minutes. This will be equal to 1 over 4 pi epsilon naught. Or actually, let me write this slightly different way. So I'll say this is 1 over epsilon naught times d cube x prime. So remember your superposition principle. If you know the electric potential due to one charge, you can add up all the point charges together and you get the electric potential due to a distribution of charges. So that's exactly what it is. But now we are talking about an integral, not necessarily a sum. It could be an integral. And electric potential due to a single charge is the Green's function. Let me call it R prime. Prime. It's R, comma, R prime. But I have to multiply each of this Green's function at each point with the charge at that point, and that's charge density. And this is integrated over all space. Try to give it some thought as to how exactly this is working, and as we do examples, hopefully this will get clearer and clearer. Like again, this is due to a single point charge, electric potential due to a single point charge. You add up all the point charges with the weight given by the charge density. And the sum of all of them is the electric potential. Remember, you have to multiply by Q over epsilon naught. Q is this per unit volume, and then 1 over epsilon naught that you multiply. In the example that we are doing, we know G, so this is equal to 1 over 4 pi epsilon naught G cube R prime of charge density divided by R minus R prime. This is the magnitude of that quantity. That's important. So let's evaluate this, right? Now this is a proper expression in terms of real solid expressions instead of functions here. Let's write this explicitly so that we know how to do these integrals. And for the case we are considering, these integrals are actually doable. So this is the x prime, the y prime, and the z prime. And even though these are integrals, so in principle it doesn't mean anything, but our understanding is that prime quantities are sources, and all through the 2 semesters we'll try to stick to this notation that prime quantity will be sources, not always, but we will stick to it as much as possible, and this will be the observation point. Like we said in the other situation, that is a point where charge sits, there's a point where you make an observation, so this will be an observation point. So this is where you're observing the potential, and the potential is being created by somewhere where the charge sits. So we scan for the charge in the whole space. So this integral is kind of scanning every point in space. This is Q times delta function x minus xa, or x prime minus xa, y prime minus ya, and z prime minus za. Don't be overwhelmed with so many integrals and so many delta functions showing up. Each of this is going to be elementary, and we want to get used to seeing these expression and seeing the meaning of this expression. The magnitude of the distance between two vectors That's a square root. Right? So this is x minus x prime square plus y minus y prime square plus z minus z prime square. That's what this is. And we are going actually from minus infinity, plus infinity, minus infinity, plus infinity. How do we do this integral? How do we do this? Let's begin with z prime integral. What is well, how do you do the z prime integral? Anyone? Yeah, so that's very good. So whenever you see a delta function, the indication is that you have to set z prime is equal to za everywhere in everywhere you see in the equation. That's one thing, and the integral is done. So I'm going to do all three integrals in a single stroke. So it's q over 4 pi epsilon naught. Note how I'm doing this. This is going to come up again and again. X integral tells me that replace x prime with xa. Y prime integral tells me that replace y prime with ya, and so on. So this is x prime here. That's where it shows up. Y prime here, z prime. That's the only place where it shows up. These are all integral. This tells you that this is an integral. And drop the integral after that. So all the integrals are done, but if I replace it, all the delta functions are gone, and I get simply this. So x minus xa now. X prime got replaced with xa plus y minus ya square plus z minus za square. That's it. So that's the simplest example one can do. The electric potential due to a point charge, and that's equal to, once you see this, oh, this is exactly the same thing that we had here, except that r prime got replaced with the position of xa, ya, za, and this is a 1 over 4 pi epsilon naught, and q over r minus r a. So if you start from here, this r prime got replaced with ra. That's all that integral did. And in fact, we know this, correct? Electric potential due to a point charge is this. This is like cyclic statement. We started with the Green's function statement that it is equal to the, by definition, it is the electric potential due to a point charge. So if you integrate it over just one point charge, you'll get back that expression. So that's good. But now we can calculate the electric field, correct? Which is actually your extra credit problem, right? You have to show that this is actually equal to the electric field. So we get the third step here in the strategy. So this is the first step, second step, and the third step here is that electric field actually is equal to negative gradient of the potential. So I'll let you guys complete this, but I'll come back and do this again. This can be shown that electric field, but this time it's shifted, right? So this is 1 over 4 pi epsilon naught, and this is q over r minus ra squared, and make it q, and there is a r hat now, which is exactly r minus ra this time. So this is a unit vector in the sense that I've divided by q this time. So in that sense, unit vector. I'll come back and start from here and do next example. I'll have 2 point charges and then basically put a whole sphere there, and then a conducting sphere, and do some simple examples there. And in your homework, you do it for a dipole. A dipole is when you have one positive charge and one negative charge. Thank you. I'll stop here.